start the last session for today for the NVMe Express. This is NVMe over Fabrics. This is a discussion of the transports. Once I get the guys on the stage, quit paneling for a little bit. We'll be able to. We're going to go through the different fabric options that people have, and this sits in the middle of 2 days of presentations that we have from all the great people at NVMe Express, starting out with a roadmap, then going to implementations, drivers, transports, and tomorrow we have enterprise arrays, appliances, and then JBoss. So we'll talk about different implementations, and we'll close up with interoperability testing at UNH and SCIA, and some others have done that work. In terms of the team, myself and Brennan Hoff from Emulex, which is part of Broadcom, but classic Emulex, focused on Fibre Channel. We have Kurt Beckman from Brocade. He's a principal architect that works on new technologies like NVMe, and he's also the author of the NVMe or Fibre Channel book. We have Fazil Osman from Brocade, Broadcom Classic. Broadcom Classic is actually the Broadcom that was before we bought Broadcom as Avago. So he's actually Classic Ethernet, doing this for a while. Nishant has joined us instead of Praveen. Praveen couldn't make it today. Thanks for making time and joining us today. So he's from Marvell, QLogic, Cavium, that family of acquisitions. Then Jay Metz, who's from Cisco, who's presenting probably more than anybody this week at this conference. And we're trying to compete, so who's presenting more sessions and stuff. But expert, has got a doctorate, has been on the CTO team, has been awarded things for presentations, all kinds of great stuff there too. I'm sure you can find his abstract on the website. The focus of the discussion today is really NVMe Fabrics, as it's really designed to be transport agnostic, with all the transports being created equal from perspective NVMe Express. It's kind of a layered model. I'll show that in a second. And we'll cover NVMe Fibre Channel, NVMe RDMA, and NVMe over TCP. You can also do NVMe over InfiniBand, but that tends to be more HPC focused and not exactly the focus of this conference. Feature roadmap, we've reviewed this several times. This is something that it's a roadmap we present. The group up here on stage is talking about the middle row, all the different fabrics options. And, in terms of shared storage, what's the value? Why are we doing this? It turns out that most of the storage shipped today is used as external storage, not in the server storage. I think it's like above 80%. And people are looking at new cost metrics for storage. In terms of the cost of data at rest is no longer the right metric for storage TCO. It's really, the metric should be around the cost of data, cost per transaction, cost of data in motion. NVMe Fabrics increases the velocity of data, makes it more used, more useful, more available. SSDs then are becoming much, much faster. A single SSD now can consume a complete PCI lane, even a Gen 8x4 lane, turns up to 32 gigs. So it can actually get tons of performance and throughput through these new SSDs in the market. And they're only going to get faster. People are still innovating and making bigger, faster storage, and so the pipe is really important in making a fast pipe. NVMe Fabrics is very simple in terms of transport layer. If we talk about TCP, Fibre Channel, RDMA, really we have an application server that sets up queues. We DMA out of it into a controller or adapter, goes across some kind of fabric transport. Each fabric transport has different characteristics and benefits. Out of the DMA back into the storage target, which looks a lot like a processor would serve anyhow. It's transport agnostic by design. So we can add a next generation fabric to it as well. And all this can be done zero copy in RDMA and or Fibre Channel. And there's actually implementations of TCP where you can do this zero copy as well. So NVMe Fabrics is architected to be very simple and very useful. And actually, one interesting thing is we're added to the Linux stack, at least, the ability to both do initiator and target in the native stack. So we talked about that before when we talked about from Dave Minturn, talked about the Linux stack and how initiate builds both initiator and target, and that's in the core stack. So you can pick up Linux, you can build yourself an initiator and target and run it over multiple different protocols and do some testing. So we see enterprise customers playing with that, proof of concepts, if you will. There's in terms of so this one I talk about some stuff. So we have Fibre Channel, we have RoCE V2, RoCE, and which are V1. We have Iwarp, InfiniBand. You can even do NVMe over FCOE for different types of applications. And now the new one's TCP, and we'll probably have other options going forward. But all these are scaled. If you look at this, there's really 2 transports available today, and that's Fibre Channel and RDMA. RDMA covers a lot of these. Fibre Channel covers FCOE. The new one that Jay's talked to on pretty much all day is TCP, which is a very interesting entrance into the market. And we share that one early because people are making investments decisions on how they build out their infrastructure, build out their solutions that leverage NVMe or fabrics, and TCP is going to be a very important part of that. If we look at the sessions today, I try to break out what are we talking about here, right? So we've talked about NVMe and NVMe-OF, and those were covered in terms of roadmap and futures this morning in NVMe-101-1. This is a session that we'll actually have recorded and available up on YouTube, so you can actually go back and review that if you haven't seen it. Today we're going to be talking about really the transport binding, the fabric, and the different types of networks that we can build with this. And that's the focus of the discussion. I'm going to turn it over to Kurt Beckman, Principal Architect from Brocade.
Thank you, Brandon, and dive right in. Running slightly behind, or maybe we were caught up already. You went so quickly there. So today's topics, we're going to take a quick look at the state of interoperability in the spec, and then we'll look at how dual protocols, which is NVMe and SCSI, will help NVMe adoption, and then take a look at a performance audit that we did recently. So why do we move to NVMe over Fibre Channel? It's like SCSI. There's a lot of parallels with SCSI, except it's tuned for SSDs, which is what our media are today, and doesn't really support the older media. It's also much better for parallelism and simpler and more efficient, and therefore faster, which is what we need these days, as our media is so much faster than it was before. The FCMVME standardization effort is overseen by the T11 group, which is under the umbrella of Insights, and they sorted their stuff out by late last year. Actually, I think it was finalized in January. And then several vendors are now shipping GA products in the NVMe over Fibre Channel space, FCNVMe, and you can see that actually over at the trade show, or at the expo. There's a rack with, I didn't get to update this slide before we printed it, but now to talk to you about dual protocol SANs. So how that'll aid NVMe adoption. So 80% of today's flash arrays that are connected across a fabric are connecting across Fibre Channel. That's where those today's vital data assets live. And if you want those things to move on to NVMe, we're going to have to figure out how to leverage that existing asset, because those storage teams are naturally risk averse. It's part of what they're paid for. Their job is to protect that data asset as much as it is to provide access, high-speed access. So in order to provide, what we want to do is provide access to NVMe at a low risk, and that means making use of a familiar infrastructure. And this is how dual protocol SANs will reduce risk and thereby accelerate adoptions. So using that familiar infrastructure to talk to your old storage and be able to talk to your new storage is going to remove a whole bunch of surprises. And as it happens, today's infrastructure already can deliver on that, today's Fibre Channel infrastructure. So you can use the same vendors, the same infrastructure vendors, and the same array vendors, HBA vendors, server vendors, and in fact, the same support mechanisms as well. And by leveraging all this familiar equipment and familiar tools and familiar teams, and really a familiar culture, it allows those storage teams, instead of pausing and thinking about it and evaluating and sending it to the lab, they can just begin to adopt in ways that they're familiar with. It's like transitioning to a new array has always been for them. It's not a big challenge. It's not something they have difficulty explaining to their management. So here's a picture that shows it. It's the same SAN, it's the same fabrics, the same HBAs, and it may be the same or different arrays, but you can speak to two different arrays from the same server and infrastructure. But we're seeing that many storage array vendors are looking at putting both protocols on the same port. it's early days, and so we'll see what emerges as best practices, whether people choose to run both protocols over the same storage port or not. It will make sense in many cases to run both protocols over the same server HBA port. Okay, and here's an interesting use case is when you've got a highly valued database running on a familiar array, SCSI array typically. Already I've talked to customers that have these very valuable databases that they're using live, and other people in their organization are saying, boy, I'd love to slice and dice that database because there's lots of value in there that I could extract in a machine learning analytics kind of a way. And, they're saying, fine, why don't you just go do a recovery off of some backup that we did a while ago, because they don't have a mechanism to run that in the SAN on the really high-speed media that they want. Well, now they do, actually, because now they can do a snapshot, clone that snapshot over to an NVMe array that's much faster. And, of course, at some point soon, they'll be comfortable actually migrating that database over onto an NVMe database. So this is all ways in which we can accelerate adoption of NVMe by using a dual protocol environment, including, for example, in this dual protocol environment, applications often have a dozen volumes, and you can migrate a volume at a time as you're comfortable with. Well, let's move the small one first because it doesn't take long. We can move it back if there's any issue, or we can just cancel the migration. And so the rollback models are very straightforward when you do all this in a dual protocol fabric, versus if you had to try and pick up an entire application and migrate to a new set of hardware with new cabling, new interface cards, etc. Okay, so I mentioned we were going to take a look at an audit report that was done recently. One of the vendors that's out there first with NVMe over Fibre Channel agreed to do an audit with us with Demartec. And so we all got together and ran a series of tests comparing SCSI over Fibre Channel to NVMe over Fibre Channel and seeing what the performance deltas were. So this is a pretty easy report to find, but of course here's a link here on the slide to help you out, demartec.com/modern-SAN. Short answer is we got over 50% higher IOPS. And just to be clear, as it says in bold there, results were for testing both protocols on exactly the same hardware, same server, same interface card, same SAN, same storage. The single storage array had 2 controllers, and so just for purposes of this testing, we did all the NVMe testing on one controller and all the SCSI testing on another controller, but they totally mix and match. So we got 58% in the most dramatic test, but over 50% in several tests, higher IOPS with NVMe than with SCSI, and between 11 and 34% lower latency with NVMe than with SCSI, depending on the test. And there are some pretty pictures that kind of highlight that. This is actually the same data, just sort of zoomed in slightly differently. So you can see when you max out the traffic on the array. This is not a full array test, so I don't mean to say maxed out the traffic on the array, but maxed out SCSI in one controller and then NVMe in the other controller. The difference was the difference in IOPS was 50+%. And then if you zoom in on the latency, you can see that there was 34%, at least 34% better latency for the NVMe protocol. So by changing protocols, changing software, doing nothing in your hardware, you get significant performance boosts and obviously can deliver more to those application users, more to those customers. And now I'll pass the baton over to Fazil.
So I'm going to talk to you about RoCE. And the way to start talking about RoCE is really to talk about RDMA. So what RDMA is basically the ability to move data directly from user space in one server to another, to user space in a different server or CPU and memory. And that's usually done by basically a piece of hardware that does that. And you compare that, so this is what you see on the right. On the left is what you see normally you do today. We're using TCP and you run through from the application into the kernel, and you run the TCP stack, you go out to a NIC. So RDMA eliminates all these layers. It goes directly from moving, the hardware moves the data from one place to another. So what is RoCE? RoCE is basically running RDMA over Ethernet, and that's Ethernet is converged Ethernet is what this is about. And there's two versions of RoCE. There's a RoCE V1 and RoCE V2. RoCE V1 was the original RoCE. It was meant to run over an L2 network, and RoCE V2 runs over an L3 network. So you can route it across. So if you go into like a large data centers where it's a big fabric that's routed at layer 3, then RoCE V2 is what you want there. And the key about RoCE is it was all designed to go for very low latency. Also important as far as what RoCE is concerned, it is really a multi-vendor standard. It is defined by IBTA. It's actually derived from IBTA drives also IB, and it's derived from the IB protocol. So we mapped it onto Ethernet. Is basically what RoCE is. So it's a common protocol for RDMA that runs over both IB and Ethernet, and you get it from multiple vendors. Today, if you look at the key guys who ship RoCE today, you get it from us at Broadcom, you get it from Marvell, and you get it from Mellanox. And also we have, and I think there's a talk later on some of the UNH testing. There's been a lot of interoperability done both at the RoCE level and at the fabrics level. But but RoCE today we have environments where you see the multiple vendors in the same data center, in the same network. So we've done testing at UNH. We also have that customers have deployed multiple vendor RoCE environments. So this slide basically shows you where RoCE fits into the NVMe fabrics. As you see, what it is you have the three protocols that are sitting there, which is Iwarp, InfiniBand, and RoCE, and they all provide this layer called RDMA verbs. So an RDMA verbs is what the NVMe over fabrics driver uses to talk to those devices. So the exact same driver that is running on top of those three protocols is just talking to verbs, and then from the verbs you map it onto the different transports that you're using. So what we've done, for example, with our RoCE is we provided verbs. We have a kernel verbs that is used inside the kernel. We can also provide it in user space for people like in SPDK, where they want to do things in user space. We can provide both user space and kernel space, and that works with all the other protocols as well. Anything that does verbs will support both kernel mode and will support a user space mode. So you can write your drivers you can run standard drivers in the kernel, and you can do SPDK, especially on the target side where people are trying to get very high performance. So the verb layer is really the key part to this whole thing. And this slide tries and shows you basically how an I/O works inside in a RoCE environment. So basically, if you look at what is NVMe, you submit you have a submission queue and a completion queue. You put a command on a submission queue, and when you have an NVMe drive on PCIe, and then the device works on it, puts the data back in your memory, or takes the data from your, depends on whether it's a read or write, and then gives you a completion. So what we've done with NVMe over fabrics to run over RDMA, we basically build what we call a capsule. And the capsule has a command and has the SGL list, for example, if you're doing a read, or it may have data if you're doing a write. And that capsule then gets pushed down over RDMA to the target side. The target side takes that, turns it back into an NVMe format and passes it on to a drive. When the drive is done processing that data, it comes back, and let's say it's doing a read. It has the SGL, so it uses that to do an RDMA send and write the data directly into the host that requested the data. So that's how you get the latency way down. There's no intermediate layers. That RDMA send writes the data directly It knows where to write it. It writes it directly into the host. And then it creates a capsule that is basically the completion, and it pushes that completion back to the host, and that gets turned into completion to the kernel or to the user space. So that makes it a very, very efficient protocol. And so this is the final slide. Is basically, well, so what's the benefits of basically running NVMe over RoCE? The biggest one of the biggest thing is Ethernet's everywhere. I mean, your data center is Ethernet, so that's the way to go. And Ethernet today is already running. I mean, we have most of our developers who are building products around that stuff are putting 100 gig interface into target device. On the server side, you're at 25 gigs, 50 gigs typically today is what most of our customers are. So Ethernet is sort of a good way to go. And RoCE, as I said, was supported by a lot of the leading vendors. In fact, I think there's some data here that came out of Crehan that says that if you look at the Onyx that have been shipped, the 25 gig Onyx, not 10 gigs, but now as people are moving 25 gigs, most of these those Onyx that was shipped in 2018 supported RoCE. That's the protocol that's there. And we've also done a lot of interoperability, both at the RoCE level and at the NVMe over Fabrics level for that. And the other good thing about RoCE, which is key for, depending on what your application is if you're looking for low latency, you're trying to get to the data fast based on what your application is doing to it. You know, we're showing everyone's showing basically sub 5 microseconds end-to-end latency over RoCE. And the other advantage is the low CPU utilization, because that's one thing you do is when you put that command, someone puts a submission command on a submission queue in Fabrics to getting it out there, you look at the CPU utilization, it's very, very low. So that's the sort of the main advantages of RoCE. It's Ethernet, it's supported by multiple vendors, it's low latency, and it's very low CPU utilization. That's me.
Okay, Iwarp is another choice for extending NVMe over Fabrics. And so let's talk a little bit about Iwarp. First, a couple of slides where I'm going to talk about, hey, what is Iwarp? Why should I care about Iwarp? With everything we are hearing about RoCE all around, why is Iwarp interesting? Let's talk about the performance of Iwarp. There are a lot of conceptions or misconceptions out there that perhaps RoCE performs better than Iwarp. So let's compare, make some good comparisons to see what we find out there. I also want to talk about some real-world use cases and finally summarize that. A lot of people in the industry say Iwarp is not an acronym itself, but from my perspective, it is RDMA over a wide area network. That's what Iwarp is. And just like RoCE rides over InfiniBand or InfiniBand rides over Ethernet and it's called RoCE, very similar is the Iwarp technology where RDMA is being transported over TCP. Right? Generally, TCP for Iwarp deployments is offloaded onto a NIC, and that NIC is called RNIC. From a concept standpoint, just like we went through the RoCE concepts, it's pretty similar. It's memory-to-memory copy. Things go over the Ethernet fabric, and it's RDMA. But having said that, let's kind of in one slide try and compare and contrast all the different types of Ethernet-based RDMA fabrics. Right? There is definitely RoCE V1, which is called RoCE, which is just basically InfiniBand over Ethernet. It's not routable, and that's why came RoCE V2, which is the routable version of RoCE heading over UDP. Now, one of the challenges with RoCE V2, especially because the transport is UDP, which does not have an inbuilt congestion management protocol built in, that there has been enhancements on top of the RoCE V2 stack called DCQCN, Data Center Quantized Congestion Notification. I'm sorry, that's quite a mouthful, but the concept behind DCQCN is to bring about end-to-end congestion management for RDMA networks. And while there have been some successes of DCQCN out there in the field, it is it's considered relatively hard to manage and get right. And there comes Iwarp then. And Iwarp, the good thing about Iwarp from a technology standpoint is that Iwarp is built on TCP, and TCP has been managing congestion in our networks from many, many decades. And so congestion is relatively better managed thanks to TCP in an Iwarp environment. Now, like we said earlier, there are questions from customers, partners, you guys in the audience. What is the performance of Iwarp? Isn't RDMA, isn't RoCE performs better than Iwarp? So let's do some quick head-to-head comparisons, and I'll help you read these charts. On your left-hand side, what we compare is kind of what is the latency, completion latency measured using our popular FIO tool that other speakers have talked about. And we're comparing here both RoCE as well as Iwarp head to head. Nothing changes, just like the Fibre Channel test that we talked about earlier. The hardware is the exact same, the server is the exact same, the same cables, the same switches, everything same hardware. You just flip the switch from RoCE to Iwarp. And what do you see? All the bars pretty much, as far as I can see, are pretty much head to head. And basically, irrespective of what block size you pick, all the way from 1K to the larger block size, both RoCE as well as Iwarp, RoCE V2 as well as Iwarp deliver pretty much the same performance. And I'll have more data to back this up a little later. Let's dig a little bit deeper. Let's talk about latency, and let's not even talk about average latency. Let's break the latency from a percentile perspective. Anybody who's familiar with running FIO perhaps has seen the output coming out from FIO with what are the IO completion latencies across different percentiles, and you will see that Iwarp and RoCE are pretty head-to-head. In some cases, Iwarp does even better than RoCE. And see, end of the day, although there can be a potential difference between the latency delivered by a fabric, RoCE versus Iwarp versus Fibre Channel, or whatever TCP, whatever next shows up, the important thing for you guys, partner, customers, engineers to remember is that end-to-end latency is what matters, right? And end-to-end latency, today the biggest contributor to end-to-end latency is the application, the software stack, the kernel, and things like that. And I'm sure things like SPDK are helping out. So don't get bogged down by just the fabric and the fabric latency itself. Now, let's talk about some kind of real-world use cases of RDMA, including Iwarp. Well, NVMe over fabrics is often talked about subject around here in these sessions and at Flash Memory Summit. There are other use cases of Iwarp, both RoCE as well as Iwarp. And one of those popular use cases is in Microsoft environments, which is with Storage Spaces Direct, or S2D, as people who know it call it. And what this is basically a hyper-converged deployment thanks to Windows Server 2012, 2016. You take a bunch of servers, each with their own hard drives, NVMe drives, flash, NVDIMMs, cluster them together to form a large pool of storage and compute, and you carve out those resources and give it to applications. The key essence of what I want to talk about here is the fabric that connects all of these S2D nodes to each other. And that fabric, by Microsoft recommendation and the most popular choice with customers, is RDMA. And what I see with customers that I talk to is that there are people who try RoCE, especially for a small scale environment, but people looking for multiple nodes of storage spaces direct tend to choose Iwarp. Just there can be scalability challenges that are hard to manage potentially with RoCE, and also it could be customer skill set in delivering a lossless network that RoCE V2 requires may or may not be present. So what I always recommend is that don't make the choice between fabrics a decision based on performance or how the stack looks like in a slide. The decision on what fabric you choose for extending your NVMe or fabric should be based on what is the culture within your company, what is the skill set, what is the installed base, what protocol are you more comfortable with, and then make a combined decision, mix that with performance. Last last two slides here. So this is a chart where, again, Iwarp and RoCE are being compared. And this is, I just picked that from a blog published online from Microsoft, where for Storage Spaces Direct, both RoCE and Iwarp are compared head to head. And the bars are pretty self-explanatory. There is no perceivable difference in customer-delivered workloads for one of the top use cases for RDMA today, which is Storage Spaces Direct, comparing RoCE or Iwarp. Finally, closing thoughts on what Iwarp is, and the credit goes to Praveen for making this slide look good. He tried to give a different twist to what Iwarp stands for, and I guess I stands for I'm one of the choices, which is either RoCE or Iwarp or Fibre Channel or whatever you call it. Wide area networks, yes, you can run Iwarp across WANs, across massive networks. There's TCP behind you. I'll make sure you get to where you want to. There is no DCP required. There is no lossless network required for Iwarp. TCP takes care of that. Once again, R is reliable because thanks to TCP. And finally, the last point, P as in performance. I think I showed you multiple different data points where both RoCE and Iwarp perform the same. So make your decision based on what you are more comfortable with and what kind of network you can deliver rather than just plain performance. Thank you.
Okay, so first of all, thanks for showing up this late in the evening. I personally appreciate you coming to our my last part of the last session of the day. And I know there's probably an expo out there with your name on it with some beer, probably. I won't take up too much of your time, but I do want to try to add in a little bit more about the TCP element of what NVMe over Fabrics is. Since we're talking about NVMe over Fabrics in general, one of the things that's kind of important to note is what does it actually mean? What is NVMe over Fabrics itself? And Brandon showed the simpler version of this slide at the very beginning of the talk. But what makes NVMe Fabrics is the fact that it's the bindings between the NVMe protocol and the underlying transport. So what that means is that there are actual rules that partake how the actual NVMe bindings are supposed to be taken according to each of the different transports. Now, what this means is that you have a ubiquity across the layer of fabrics, both above and in the bindings themselves. But those bindings actually are the glue that holds the NVMe to the actual transports. And what this means is that you can't necessarily just throw NVMe commands onto an Ethernet wire and expect it to work over time. It can work now. It can work shortly, over a period of time. But eventually, you're going to get errors. Eventually, you're going to get problems. Eventually, you're going to have to recover, and eventually, you have to be able to renegotiate the relationship between the host and its corresponding storage target. That's what NVMe over Fabrics does. It identifies and defines those bindings. It identifies the way that data is supposed to be kept, and it identifies the way that data is supposed to be transmitted, identifies the authentication methods, how you're going to keep things integral to the relationships and so on. So it's important to note that while we're talking about Fibre Channel and while we're talking about the RDMA versions and TCP, they all have their own binding specifications that make it part of NVMe over Fabrics. Now, what that means is that even though there are slight differences inside of the NVMe over Fabrics, what really becomes a decision tree for that point is whether or not the gestalt of a storage network fits in with a particular use case. There are sweet spots for all of these listed above. Now, up until recently, we've only had two different models for how we actually have those bindings into the Fabrics transports. That was the RDMA base, which of course had the RoCE, the Iwarp, and InfiniBand and ICER, which is just effectively the way that the RDMA verbs and metaphor and semantics get applied into the bindings, and we had Fibre Channel. Now, the reason why those were important, the reason we haven't had a chance to go into any of the technological discussions, but it makes a difference as to how the data is moved from one memory space to another. PCIe does it one way that's very similar to the way that RDMA does it in terms of transferring memory from one buffer to another. Fibre Channel and TCP have similar categories in the way that they handle the memory transfer between buffers. So there's more than just whether or not you're friendly with certain things. What's that?
Good. That's good.
Okay.
We're adjusting the screen.
Oh, more screen adjustments? See, isn't it? It's a pain in the butt, isn't it? Okay, so why do we want to have NVMe in the first place? I mean, NVMe over TCP in the first place. I mean, we do have the TCP option with Iwarp, but that's where we have the breakdown of, well, do I want to just use a vanilla TCP transport for moving the commands around, or do I want to associate RDMA verbs with that? And if I don't want to use an RNIC for this, can I just use a standard NIC? Well, right now the answer is no, because there's no bindings for it. That's what NVMe over TCP is supposed to allow us to do, to create those bindings and to create the definitions for how the memory transfer is allocated using a TCP standard. The idea is that we're creating a one-to-one relationship between the TCP sockets and applying those queue pairs through those sockets so that we essentially associate a session with an NVMe queue pair. It seems intuitive once you start to realize this, but it's not by any means a natural progression for what we think is supposed to be going. There are currently on the market non-standardized approaches for dealing with TCP and NVMe, but that's why I'm making such a big deal out of this. You can throw NVMe commands into a TCP packet. It's not a big deal, but when things go wrong is when it becomes a big deal. Okay, so what NVMe over TCP is allow us to do is to use the error recovery mechanisms in TCP and the bindings for being able to associate relationships between a host and a target simply using the standardized TCP protocol. It's more than just putting things into a packet. It has to do with the way that we recover from that as well. Just the same way that we have to do it for Fibre Channel, just the same way that we have to do it for RDMA-based approaches as well. Now, okay, so what we do is effectively we establish a creation point of an admin queue pair using an NVMe TCP command. There's a well-known port for TCP NVMe. So basically what we do is we associated the TCP port 8009 for the actual sessions that go across the TCP layer. Did you break it?
I fixed it again. It's coming.
Dude, you reset it. All right, you're not allowed to do this anymore. That's okay. I don't need the slides. Okay, so basically what we need to do is we need to have a host and we have a target, and those hosts and targets are connected via a TCP network. And effectively what we do is we are allowing a TCP session to create that queue pair that goes between those two devices. It allows us to separate out different types of sessions according to whether or not we're talking about data or management. So we can do a control plane using a much narrower link. For example, we could use a 1 gig link for admin queues or for management queues. So we could run NVMe-MI on one 1 gig link or on VLAN, and we can do another admin queue pair on another one. And that makes it really simple because now we don't have to have in-band management. So a lot of the advances that we've been making for NVMe-MI, for example, are now even more applicable in a TCP environment because you're not embedding the actual management commands of the chassis inside of the data stream. You can have completely separate TCP sessions for your admin commands, your MI commands, and then you'd have another complete data link for the heavy throughput that you're looking for in an environment. This becomes really useful in very big environments, especially extremely large environments. Because what winds up happening is that if you have a massive network and you want to have the kind of block storage that you might find in something like an iSCSI environment or a hyperscaler environment, that way you can actually associate some sort of software-defined layer to manage all of the IP addresses because it's also on a well-known TCP port, and you can monitor what's going on across the network with a network analyzer. And then you don't have to worry about any specific hardware, and you can add in nodes as you wish and as you need. It's just simply by being able to run the software on the host to be able to connect to a known port and then be able to handle that management through a software layer. Now, what does this mean in terms of performance? Well, in terms of the actual stack, you're going to get a little bit of an additional latency issue from one side of the TCP stack to the other side of the TCP stack. That's normal. That's nominal. As Nishant was talking about, when you start to putting them side by side in a perfect world, you're going to get very little variety and disparity in terms of the actual performance. But like any other storage network, you're also going to have to keep in mind that there are other things going on in the network other than just NVMe, right? So no, you don't necessarily need to have DCB. That's not necessarily something that you must have in order to get it to operate. But if you're looking at doing this, you have to keep in mind the way that TCP networks are typically created. So a TCP network doesn't necessarily mean you have no problems, right? Trust me, I work for Cisco. We have a lot of customers who don't know how to put together a TCP network in such a way that they don't have any problems. That's why people get CCIEs and get paid a lot of money for them. I'm not one of them, but I've heard that's happening. Okay, so when we start to talk about being able to deploy this and we try to find out whether or not you should do this, it's the same rules that apply in a storage network that acquire anywhere else. Now, one of the big questions, and this was kind of alluded to but not actually talked about, and it may sound like I'm trying to say you don't want to do TCP, because that's not true. It's not true at all. But one of the caveats that we have to have is whether or not you actually have the variance of latency in your network. That's the big problem, right? So if you've got a really large network and you're talking about multiple hosts and you have your host several hops away from your storage, that's not necessarily best practices in any storage network, right? Generally speaking, you want to keep your storage as close to the host as you can, physically. And that doesn't necessarily mean that you want to go block-based storage from a host to a target over a WAN. Sorry, just not best practice. All right. So what you need to do is you can't necessarily break the rules just because you have one part of the layer now be a little bit more convenient. If anything, it makes it more important to make sure that your overall topology and architecture is proper. The other thing to keep in mind is what are the application requirements. Your application is always going to be king. When you start to apply NVMe in a specific type of applications, you have other things that are running at the same time. What are your east-west traffic requirements on a TCP network? Right now, the east-west traffic requirements are probably far more significant than what they may have been just 10 years ago, right? And now you have to contend with that traffic inside of a TCP network because that's the way that LANs work. So ultimately, you want to make sure that the contention that you may have is mitigated in some fashion, whether it be through a proper architecture, it could be cloths. Well, at least we got to the desktop. I'm still presenting. I have no idea what's going on. You know what? Don't worry. Don't worry about it.
Keep talking.
Right. Do you need the slides, or, I mean, am I making sense? Or are you sleeping? Okay. There's always email on your phone if you're bored with me. But effectively, the idea here is that when we have really large environments like hyperscale environments that don't necessarily care about the latency because they're only running 5 applications across the entire data center, it could make a lot of sense. Or if you're running in a hyperconverged environment where the TCP element is really critical, but it's in a restricted network, that also might make sense. Right? It all depends upon what else is happening at the same time, because storage is not the only thing that's happening inside of a network. What you really need to be careful about is when you start to extend, because you can, the distance between a host and its corresponding storage target. If it's in the same rack, if it's in the same switch, you're going to get really close numbers no matter which protocol you wind up using. Right? So it all depends upon it depends on, as Kurt was talking about, it depends upon your end-to-end qualification requirements. It depends upon your teams. It depends upon your bursty traffic, your elephant flows, your mice flows, whether or not you're talking about large sequences of data, really small transactional data, those kinds of things, and how far apart and how much congestion you're going to have to deal on your network. If you have large TCP networks and you're gluing in a clause type of a system, and you don't keep the storage in the same environment or the same rack or in the same node or the same pod as your hosts, then you'll have to keep in mind that you probably have to use other forms of network mitigation strategies, whether it be DC TCP, data center TCP, or DPP, which is deep packet prioritization, any kind of QoS policies, any kind of class of service policies. The typical thing you'd need to do to improve iSCSI traffic, for example, would be applicable here inside of a TCP NVMe stuff. But ultimately, the idea here is that we're adding additional networks to go into the NVMe spec so that you can make a choice based on the normal ones, but none of these solutions are no-brainers. Don't ever get the impression that just because of the fact that something is new and nifty and flashy, that it's always going to solve all the problems in the data center, right? We still have that one job in storage, and that's give me back the bit I asked you to hold on to for me. And anything, and I mean whether it be in a TCP network or whether it be in a Fibre Channel network or whether it be in an RDMA network, anything that prevents that from happening is going to be a bad thing. So we've been all working really hard to make sure that that doesn't happen. And so all of these things have their own caveats that they have to keep in mind and have to keep track of. And that's my spiel for this. You want to come and rescue me?
There's also contact information that we'll have. I don't know if that popped up there. We should just pronounce it dead right now. Oh, I do have one question though. I thought, 2 years ago we just announced a standard for NVMe-OF. A year ago we were all up here talking about, hey, wouldn't it be cool to have devices? Now we have devices in the market. We have products in the market. I figured to each one of you talk about where you see adoption of the different technology. What are the use cases? What do you typically see as the value or benefit?
Can I start with that? Do you want?
You start?
Yeah, I'll just start. Believe it or not, I think that the industry that has the furthest progress is actually Fibre Channel. And part of that has to do with the actual ecosystem is a lot smaller, and therefore more of them can get their acting gear quicker. But the other thing that Fibre Channel has that we're still working on the Ethernet side is things like discovery, and the end-to-end qualifications. Those are things that are all part of the parcel of actually making it. So we are getting a lot of people who are interested in Fibre Channel from the NVMe perspective because much of the heavy lifting is already done. Right, so we've got the ability to create very robust fabrics up to thousands and thousands of nodes, which doesn't exist right now in the Ethernet world or the InfiniBand world from a storage perspective, right? So we're seeing a lot of interest in the Fibre Channel side. Now, in the single rack environments, we're getting a lot of interest and adoption from startups who are basically talking about top-of-rack solutions, and as long as it doesn't go outside the rack, right?
Yeah, a single switch.
Right, a single switch, talking to storage at the very top of the rack is where we're getting, and we're seeing a lot of different options and different types. The RoCE V2 is very popular. RoCE V1 not so much. And even a few Iwarp solutions as well that are based generally at the top of rack. So a lot of the routability questions that are coming up haven't yet met the deployment side. Generally speaking, from my experience in the different things, but that's my first go.
Yeah. Just to add, we do have solutions in market for InfiniBand, so NVMe or RDMA for InfiniBand. So they're not on part of this panel or this conference, but there's also solutions in market there. So I'll pass this on to the next panelist. Might need to stand.
So I will support, I think, what Jay said. What Fibre Channel has today is the customer's trust in transporting their storage over Fibre Channel, right? And that's why we see a lot of interest from customers who are comfortable with Fibre Channel, have installed base of Fibre Channel, very comfortable with evaluating FC and NVMe. Ethernet, I think, is a great choice for fabrics, but I think a lot of the RDMA protocols, including Iwarp and RoCE, have to prove to the customer that data can be protected and make sure that every bit and byte is transported to the drive and back. So that trust factor still needs to happen, at least in my opinion. But I see it in kind of two segments. The people who are going to deploy more software-defined storage, perhaps even some hyper-converged infrastructure, may likely choose some kind of RDMA protocol and even TCP to scale out NVMe. The typical enterprise customers, all flash array guys, at least for the next few years, likely to stick around with Fibre Channel. That's what I think.
Your answer can't be Fibre Channel.
What's that? No,
I know it won't be, but.
So I'll tell you what I see on the Ethernet side. I think on the Ethernet side, we're seeing exactly what Jay said, is that people are starting to deploy them in the rack. I think across the data center is a long ways away. Because what people want to do is they want to take they used to have, SSDs are getting so big, and they're still not cheap. So you put them on a server, and if you're not using it, it's just sitting there. So what they're looking for is, if I put a box down there, I can put them down there, and I can allocate those SSDs. We're seeing that use case. The other use case we're seeing is people that are doing basically analytics, where they want to put the data down there and share it across 40 servers in a rack kind of model. I think that's the two kind of use cases we're seeing. And that tends to be, RoCE works fine for that. There's no issues with going across a big, large fabric and worrying about congestion and that kind of stuff at that level. So that's kind of what we see. You can't talk about Fibre Channel.
Only so many protocols.
Yeah, what can I talk about? So in fact, I read the question slightly differently. I didn't think it was a question about where are we seeing adoption in terms of protocol, but where are we seeing adoption in terms of use case? So I'll talk about that. It does seem like there's two ways to look at where people are coming at this from. There's always some application that wants to run a little bit faster. I think there's a little bit less of that right now than there has been traditionally when we were dealing with spinning disk, and that was kind of holding up the show. And so anyway, you could speed up spinning disk with SSDs or other things. Now, since everybody's gone to flash, really anybody who cared about performance went to flash a while ago, and we've been giving them a performance pretty aggressively. It's not quite as much of a hunger for that performance, the performance that NVMe gives from that side of the house, but there is some, and when you ask customers, they're talking about, just as before, they're going to take their existing applications and run them faster. So that's definitely happening. But in addition, there's a bunch of applications, a lot of AI and ML and deep learning, machine learning and deep learning, that is so performance and data hungry. The performance was so high that if you had 200, 500 microseconds latency, that was an impediment, and they would just try and cram as much as they could into direct attached PCI-based storage. Now, as we're seeing with NVMe over fabrics, there's much more investigation, because the problem is that you run out of scale in that case, and there's other issues with direct attached PCI-based storage. So now these applications are seeing really low latency in a fabric-based opportunity to scale up a much larger data structures and so on, and potentially even take advantage of some of the features that you get in array-based storage as well, replication and maybe dedupe potentially, and so on. So I see that there's newcomers to the use case or to the fabric in the form of use cases that were only running direct attached, and then there's the classic model where you always want something to run a little faster than it ran last week. So one of them we're very familiar with. I always want to go faster than I went last week, and then the new one of these big and fast-growing applications that have been running on direct attached NVMe now are saying, you know what, I've got enough caching and whatnot. I can give up a few microseconds and go across the fabric in order to get 1,000 terabytes, which doesn't fit in my server. So, yeah.
Well, I'd like to thank everybody who joined us on the panel and everybody that joined us in the audience. Thank you for your time, everybody at the podium. But thanks, and everybody enjoy the show. And we come back tomorrow. We're going to start with NVMe over Fabric's enterprise arrays with NetApp and IBM. Then we're going to talk about really the whole idea of Ethernet and a rack, how those products fit both as appliances and then as JBOFs. And so we'll have those sessions, and the last one we'll be wrapping up with interoperability. And for the sessions online, we'll actually have these all on YouTube as well. So if you miss it at the show, you can catch it later. Thank you for your time.